Cool. Can everyone hear me? Yep. Cool. I am Emma. I'm going to be talking to you about Introduction to Neural Networks. It is very much an introduction, so if anyone here is an expert in neural networks, uses them a lot, you're probably about to be quite bored. I'm sorry. I won't be offended if you leave. I'm Emma. I'm a software engineer and team lead at a company called CMR Surgical. We make robotics to do keyhole surgery. They're paying for me to be here, so it feels like they deserve a mention. We are hiring, so particularly DevOps, test engineers. We would love to hear from you. Right, but what does that have to do with neural networks? Thankfully, nothing. We're not yet letting the robots control the scalpels they have in your body, don't worry. I am weirdly talking about neural networks precisely because I am not an expert in neural networks. And I was fed up of reading about them and hearing them as buzzwords everywhere, these magical things, and wondering, great, but what actually is a neural network? What does it do? Like, why does it work? So I thought I'd quite like to see that talk, so I would try and research it. So broadly, we have this idea of biological inspiration for neural networks. So you've got neurons in your brain firing, sending signals, and it calls the next one to fire, and so on. So we can imagine a sort of artificial model of a neuron. This is kind of like the old school, quite retro idea of one. This is PERCEPTRON. And you have some weighted inputs to your neuron. And then the neuron fires if those inputs are over a certain threshold. So we've got a step function. So if the sums of these weighted inputs plus the neuron's bias is over 0, the neuron fires. If it's not, it doesn't. And to introduce some terminology here, because I'm going to get really sick of saying sum of weighted inputs plus bias, we're going to call that quantity Z, the activation input. And then we're going to say that when you apply an activation function to that, which in this case is our step function, but we'll get to some other ones later, you get the activation output, which we'll call A. And you can think of things like, so if your weight on a particular input is large, that means you're kind of, you're giving more weight. You're making that input more important, so it's going to have a bigger impact on whether the neuron fires or not. And similarly, if you give it a lower weight, then it won't have as much of an impact on what happens. And we can connect these neurons up. So this is a network of them, and we've got 3 layers here. We've got our input layer, which these aren't really neurons. They're drawn like that by convention. This is just our input value. The arrow you see going to the next layer, it's the same value going to each of them. It's just easier to draw on a diagram than one arrow splitting out. And what happens is that value gets passed into the next layer, and then that neuron decides whether it fires, and then its values get passed on, and so forth. We feed forward through the network. And you have input layers, your inputs. You have output layers, where you look at to see what the result of your neural network, what's it told you, see what the activations were there. And then anything in the middle is a hidden layer. Now, there's nothing special about a hidden layer. It's not mystical, magical. It's just a layer that isn't input or output. And what we have is a fully connected network here. So if you look at each layer, if you look at a neuron in that layer, it's connected to all the neurons in the next layer and all the neurons in the previous one. Now, what's interesting about this is if I go back to this perceptron, if I'd have drawn this with 2 inputs rather than 3, I could have quite easily made this into a NAND gate by picking my weights and biases. And if you can construct, NAND gates are sort of universal units of computation, so you can construct more computationally interesting things from them. So if my perceptron's basically a NAND gate, and I can connect and make a network of them, then I can create more computationally interesting things. Now this for me was quite an insightful thing to read when I was like, oh, that's sort of what a neural network is. It's reassuringly familiar and also sort of disappointing in terms of neural networks, especially this cool, amazing new thing. It's kind of a bit of a killjoy that actually it's just sort of the same things we're used to. What's exciting about this is that unlike logic gates where I have to lay them out, with this, the network can learn the weights and biases. So we can not have to sort of lay all the logic of our computation out. This can learn how to do it. But if I want to learn these, then using step function as my neuron is going to not be very helpful to me, because what I want to be able to do is gradually change my weights and bias sort of iteratively do so and see what change that has on the output. If nothing happens for ages and then suddenly it fires and then it causes a cascade of other things to fire along, it's not great for learning. What I want is something more sort of gradually changing, more continuous. So we're going to switch to using sigmoid neurons. So these are pretty much the same as before, except instead of our activation function being a step function, it's now this sigmoid function. Right? And this just means that we've got this nice continuous graph. We can see the limits of very large activation inputs, very small ones. It basically behaves the same as perceptron. But now our output is no longer 0 or 1, it's somewhere continuously between that, and similarly for our inputs. So we now have enough building blocks for me to actually make this into an example, something more concrete. So I'm going to do the most ridiculously stereotypical hello world example of neural nets, which is classifying this data set. It's called the MNIST data set. It's a collection of handwritten digits, and they're all tagged with what what number they're supposed to be. It's split into 40,000 training examples and 10,000 test ones. That split is important. So you want to train your network on one set of data, crucially with handwritten digits written by a different set of people, and then test it with somebody else's handwriting, because you want to check that you've learnt how to recognize numbers in general, not just specifically the numbers you've already seen before in that person's handwriting. So all of these images in the data set, they're all centralized in the middle of their sort of square, and they're all sort of scaled to be roughly the same size. So important to know for how it works. So how would we go about designing a neural network to classify, that we could train to classify these digits? So the input and output layers are reasonably easy to pick. These kind of reflect the problem. So each of the images is 28 by 28 pixels. 28 squared is 784. So I'm going to have 784 input neurons. Each of these corresponds to kind of the grayscale value of that pixel. So if it's white, 0, going all the way up to 1 for black. My output layer, again, I can pick to reflect the problem. So I want to recognize the numbers 0 to 9. So I'll have 10 output neurons labeled 0 to 9. And we will interpret the prediction of this network, or the classification of this network, by looking at that output layer and seeing which one of the ones it's given the highest output for. And we'll say, well, if the one corresponding to number 4 is the one that it's given the highest value to, then we'll say it's saying that this digit is a 4. How I pick all the layers in between is a bit more difficult. It's a bit more of a kind of nebulous problem. There is no good answer for how you pick your first guess. You pick something, probably something relatively simple, and then you iterate from there. So you might say one or two hidden layers or something like that. So how do I go about learning all these weights and biases then, so this does actually something useful when I feed it in the example? So I need to train my network. So as I said, we've split the data into training and test data. And what I'm going to do is define a cost function for the performance of my network's classification on the training data. So you can pick a different, whatever cost function you like. I'm going to go with a quadratic cost. It's nice and simple. So we're just going to measure the difference between what the network predicted and what the actual result was, and average that out over all the examples. So y of x here is what our network should have predicted. So if we go back, say it should have been a 4, we'd be wanting the activation output of that 4 neuron there to be 1 and all the others to be 0. We'd have that as a vector. A is the vector of activation outputs I actually got. And this cost function is going to be a function of all our weights and biases. And we want to find those such that we minimize this cost function. So those of you who've done a bit of maths might be thinking, I'll get some calculus out, a bit of differentiating. There are hundreds of thousands of lines there, hundreds of thousands and weights and biases. Analytically, this is going to be impossible. So we need some kind of numerical method for doing this. So we could use gradient descent. Picturing space in thousands of dimensions is pretty difficult. So let's imagine the cost is a function of two things for now. So we're back to our nice, friendly, three-dimensional space. In that case, you can imagine a kind of contour map where you've got mountains where the cost is really high, valleys where the cost is low, and you want to go and find a valley. So you could do this by saying, wherever you are now, you look around you, you find, okay, that direction right there is the steepest way I could possibly go down. You take a step in it. And you say, okay, now where's the steepest way I can go? Okay, that way, take a step, and so on. You will eventually get to some kind of value. It won't necessarily be the lowest one on the map anywhere. You're not going to, probably won't have found the global minimum. That would be very difficult. But you'll have found a minimum, which will probably be good enough for us. Clearly don't do this in real life, by the way. Algorithms that tell you to jump off cliffs are not to be followed. So what we're going to do is we're going to iteratively update our weights with this gradient descent method. So we're going to take, say we've got a weight, WK, and we want to go to the next version of it, a new and improved WK prime. We're going to take the current value of that weight, and we're going to take a little step down the gradient. I'm going to take the size step we should take. It's another interesting question. So I'm going to represent that as the learning rate. So I put it there as an eta. It's kind of a Greek letter that looks sort of like an N. And if we pick this to be too small, we will get where we want to go, but we will get there very, very slowly. If we pick it to be too large, we may not find a minimum at all. We'll overshoot and perhaps never get there. So this allows us to learn the weights and biases. There's one fundamental flaw here, though, which is we've no idea what these gradient terms are. How do we find it? So as I said, analytically, it's a bit difficult. There's too many variables here. So we can use a thing called backpropagation. So we're now up to about the 80s in terms of neural networks. This is the big thing for neural networks in the 80s. And basically what we can do is we can take one of our training examples. So say that's the inputs for this particular training example. We can do a forward pass through the network. So using the current weights and biases that we've got, so we probably randomly initialize these to start with, we get these are the activations going through. We know what we want this to be classified as. So our target output for this particular one is that the top output neuron here would be activated with 1 and the others with 0. This means we know what the errors are. So we can start going backwards through the network and working out what the errors are. So here I want the top one to be about 0.2 higher. I want the middle output one to be quite a bit lower. The lowest one there to be a little bit lower than it is. What that then allows us to do is then go backwards further. So for instance, if I take this top one here, so I want that value to be higher. How could I do that? So if I left the weights and biases fixed at their current values, then I would need the next layer's back's activation outputs to be changed in that way. And I can think about the same thing for the other two output neurons. And then we can take the average of that. So that's kind of, on average, that's what we want the change to be in the previous layer, keeping the weights and biases fixed. And I can take that back to the next layer, so work back through. So this is what I'm saying I would like, in order to minimize the cost, so which is what we're aiming to do here, if I could change the activations of these neurons like this, that would allow me to do that. Now this is only for one training example. So say we have another couple of training examples. We get this. Again, we take the average. So over my whole training set, this is the kind of change that I want to see. I can get rid of the neurons in the diagram and destroy it as a matrix. So I'm going to call this delta. This is the changes I want to see to these activation outputs. Computers, you're probably not going to have a lot of arrows. You probably have matrix of numbers like this. So we're starting to move towards maybe some equations for what we could use. We need to do a bit of notation first. So I'm going to label the output layer as capital L, elf layer. The other layers are going to be lowercase elf layer. Now, here it happens to be the penultimate layer. Don't read into anything to that. I could have as easily called the second layer the elf layer or something like that. And then I'm going to label my neurons in that layer as, say, I've got here the JAF neuron in the elf layer. And it's got a bias BLJ. It's got an activation input ZLJ, activation output ALJ, error delta LJ, and so on. The interesting notation is the weights between the layers. So say if I've got this JAF neuron in the elf layer, KAF in the L-1 layer, then it's WLJK. So once you remember what the notation is, it makes the equations easier to follow. Speaking of, I've just split the room in two, is my problem here. Half of you are going, I want to see the proof, and the other half are going, wow, that's a lot of maths. So I'm going to try and appease everyone. So if you want to see the proof, the URL is there. It's in far too small writing. I have put it at the end as well in bigger writing. Pretty much, you can think of it as when you change your weight, it's going to have a knock-on effect, changing the next activation input, which is going to change activation output, and so on throughout the network. So you basically just apply the chain rule and use a bit of linear algebra, and you get to this. For the people that don't want to see the proof, really, really don't want to see the proof, all I can say is the main thing is I think in the box here. So we've now got a way of calculating the gradients for when we change a bias or a weight. And we can calculate them in terms of these delta terms. And the things at the top tell us how to calculate the delta terms. Conceptually, the thing I want to take away is the thing that I just showed the pictures of what backpropagation actually means. Because I'm really trying to explain what the concepts of things are rather than like the mathematical details. So if you understood the diagrams, then the equations are just the equations. But equations are good because they allow us to write code. So in pseudocode, this is sort of what backpropagation is. Hopefully it's big enough. So I'm going to take all the examples in my training set. I'm going to, for each one, feed forward through the network. Then I'm going to work out what the error is in the last layer. And then I'm going to go back through the layers, backpropagating those errors and working out what my delta term is. And I can use that to then update my weights and biases because I've managed to calculate the gradient term. I'll give you a second on that slide. So, isn't that going to take a while? I said there were 50,000 examples in that training set. Yes, it could take a while. It's not as bad as you think. So the key thing about the backpropagation is it allows you to only have to go through the network twice for each training sample. You go once forward, once backwards. If you compare that to what they had before they thought of this algorithm, you had to, imagining a change to one weight, you'd have to try to make a little change to the weight, go through the whole network, feeding forward with your particular input example, see what effect that had, then repeat that for all the training samples, then do the same thing for the next weight, and the next weight, and the next bias. This, at least, you only have 2 passes through the network for each training sample, so it's a bit quicker. You can also use a lot of sort of linear algebra libraries and stuff to parallelize a lot of this stuff, GPUs and the like. But still, it is quite a few data points, to say the least. So what we can do, instead of doing our gradient descent using all of our training set, we can do something called stochastic gradient descent. So pretty much the idea is that rather than trying to find exactly the right gradient to go and take a step down, I'm going to be happy as long as I got roughly the right direction. So I take a subset of my training data, sort of size M batch, and I work out the gradient across that set, and it should be approximately the same as the total gradient as long as I've sort of picked a sensible set. So the pseudocode for that then is that you split your training data into random batches, and for each batch you work out the approximate cost gradient, and you update the weights and biases according to that. Iterate for your batches. Once you've used up all of those, or your training data, you go on to what's called the next training epoch. So we now take more random batches from the training data set, so we kind of mix up the batches. Diagrammatically, it looks sort of like this. So whereas gradient descent, you can see I'm always stepping perpendicular to these contour lines, always going down the steepest route. Stochastic gradient descent, that's slightly more like I'm wandering home from the pub. But you get more or less to the same place. And the important point is that each one of these steps is quicker to do, because you have much less to calculate in order to make it. So let us see some code for a neural network. Now, clearly, I'm not suggesting that you should implement your own neural networks. There are libraries for this. But as an education exercise, actually, it's quite good. So if I start this running, so what I'm going to do is load up the MNIST dataset. I'm going to create myself a neural network with I've got 784 input neurons, 10 output, and I've got one single hidden layer with 30 neurons in it. I'm going to train that network with stochastic gradient descent, and then I'm going to evaluate it against my test data and hope that it's worked. So I should say, by the way, that I wrote this after reading an online book about neural networks, which I'll link to at the end. So it is very much, I closed it before writing this, but it was still in my head, so the credit is probably due to Michael Nielsen for quite a bit of this. So we initialize our network. So we have some layers, we've got some arrays of biases and weights, and then when we come to train it, so we do kind of what we were talking about before, so we have a number of epochs. So I've kind of defaulted this to 30 epochs. All of these parameters, by the way, so epochs, batch size, learning rate, you've almost given yourself another machine learning problem in terms of how do you pick your hyperparameters. You almost do a grid search or something on that to pick those. But these are some good values that seem to work okay for this. So we pick, we go into our batches. For each one, we update our weights and biases, which we do by doing backpropagation to work out the gradients, and then using gradient descent to take steps down that gradient. Backpropagation, so again, we feed forward for our network, and then we calculate our errors going backwards, starting from the last layer, going back through. I'll skim past the bug that I noticed 2 seconds before coming into the conference room. That's pretty much it. So evaluating it, we just want to see how many were correct, really. And it's correct if its classification matches what the training data was labeled as. So, and we are at epoch 22 out of 30. So I will flick back to the slides to show you a couple of things while it's finishing. So resources, I mentioned a couple of times. So this first link, I can't recommend enough. So as I said, I put this talk abstract in because I wanted to finally actually learn about neural networks. This top link here is a brilliant 6-chapter book about neural networks and deep learning. I read that sort of cover to cover in the last couple of days, and it's really good. It covers a lot more things than I managed to fit into this 20 minutes, so go on to think about things like convolutional neural nets and recurrent neural networks. Problems with neural networks, you've got these hyperparameters to tune, you've got issues when you get lots of layers, you've got issues with overfitting. It goes into quite a bit of detail. And these YouTube videos, this particular one, the playlist there, particularly the animation of how backpropagation works, I found very insightful. As I said, there are actual libraries to do this rather than writing your own. It's a useful education exercise, but otherwise there's very powerful libraries out there. So this, for instance, is TensorFlow and Keras. So I'll go to full slide. In not very many lines of code, you get some pretty powerful features here. This gets you something like 98% accuracy, which is pretty good. Some of the digits in the data set I would look at them and probably pick the wrong number as well. And this there's lots of features in here that we didn't talk about. So there's different forms of activation function and cost function that you can try. So I would say check those out. And hopefully, if we go back, it has finished. We got 9,330 out of our 10,000 right, so about 93% accuracy. So, yeah, pretty good. Thank you. Yeah, sure.
Okay, it looks like we actually have got time for about one question, so if it's a nice brief one, do we have anyone who's got a question? Oh yes, okay, we have one here. Okay.
Say in your implementation you had one hidden layer between the input and the output. What's the effect of having more or less hidden layers, apart from the fact that obviously the backpropagation will take longer? What's it actually doing?
So the way people try and think about this is, and they're not actually sure if this is true, because why neural networks work is actually an open research question, is that the more layers you've got, it's almost like being able to build up layers of abstraction in code. So it's kind of easier to do a bitwise multiplication with a couple layers of logic gates than it is to do it all flat in one layer. So the idea is that you might say in your first layer hope to pick out some kind of feature, and the second layer like combine those together and see patterns and so on. Is the hope people have, but then when they look at what the map of the activation output for it, and sometimes you kind of see, well, is it actually doing that? One thing particularly about having more hidden layers is you get a problem with gradient instability. So because of the sort of chain rule aspect to it, you've got lots of gradient terms multiplying. So as you go backwards, you've got all these terms, and if they're all smaller than 1, you get diminishing gradients, and you have something called the vanishing gradient problem, where the later layers of the network are learning much quicker than the earlier ones. Or if you've got terms bigger than 1, you have the opposite problem. You've got an exploding gradient. So there's kind of, that can be a problem in deeper networks.
Okay, fantastic. Well, thank you very much for that very informative talk. Let's thank Emma one more time. Okay.